Alright, so this next video is going to focus on precipitates, when they form, why they form, and why sometimes they don't form. We did a lab with calcium hydroxide a while back, and you added drops of constant amounts of hydroxide to diluted amounts of calcium until the white precipitate disappeared. And then you did the same thing where you diluted the amount of hydroxide you added and added it to constant amounts of calcium until your precipitate disappeared. And what was happening was that initially the amounts that you had present of both the calcium and the hydroxide ions, the concentrations were greater than the KSP for that particular solid, calcium hydroxide. And so it forced the precipitate to form. Because the concentrations of the products were greater than your K, it forced the equilibrium to shift back towards the reactant side where you had your solid. Remembering that we don't include pure solids or pure liquids into our equilibrium expressions. And that when we reached the point where we no longer had any precipitate form, that was the point at which we just had ions present. Our Q was either equal to or less than our KSP value, which is why we didn't see any of the solid produce. So your KSP expression is just taking that solid and splitting it into its ions and raising each ion to its coefficient. Then that's called your solubility product constant. Fancy schmancy. So initially you don't have any of the two ions. You just have a certain amount of solid that you've added. Because you don't have any of the two ions, the amount of your bismuth sulfide has to decrease, and the amounts of your bismuth ion and your sulfide ion have to increase. They do increase proportionally based on their stoichiometric ratios from the balanced equation. And so at equilibrium, which again doesn't have any of the bismuth sulfide present because it's a pure solid, you would have 2 times the amount that dissolved of the bismuth and 3 times the amount that dissolved of the sulfur. So the S is representing the solubility of our solid because that's the one that changed by X. And so X and S in this particular type of equilibrium are synonymous. S just represents the solubility of the initial ionic compound that went through dissociation. So if we know what the change is, we can determine how much of the original ionic compound was able to dissociate by solving for just the base value of X, or in our case S. So solubility is determined by using your KSP value as well as the amounts of the ions that were produced. And because we had each of the ions raised to their coefficient, it's not just 2s, it's 2s squared. It's not just 3s, it was 3s cubed. And that gave us a ratio of 108s to the fifth. So if we want to calculate what S actually is, we know it's half the concentration of the bismuth ions that were formed, and it's a third of the sulfide ions. Or it's the KSP over 108 raised to the 1/5. Because KSP is constant, it's going to make finding that solubility fairly simple. However, if you have one of those two ions present through a common source of bismuth or sulfur ions, the S can change. It can increase or decrease based on if something is added or if something is removed from your mixture. So the first thing we're going to do is write solubility expressions for these two particular ionic compounds. So CeIO3 would break into cerium ions and iodate ions, Ce3 plus and IO3 minus. But because there's 3 IO3s present in that ionic compound, we would need to change the coefficient to 3. And so the KSP expression for this particular ionic solid would be those two ions, the cation and anion, making up the solid, with the anion being raised to the cube power. For aluminum sulfide, it would split into aluminum and sulfur ions, but aluminum has a +3 charge Sulfur has a -2 charge, and we would need to account for the number of ions present in that ionic compound, 2 aluminums and 3 sulfurs. So the KSP expression would be aluminum raised to the second power and sulfur ions raised to the third power. Okay? So in this particular one, I'm asking you to calculate the KSP of lithium carbonate. You are told the concentration of carbonate is 7.4 times 10 to the negative second. And so if we know what the concentration of carbonate is, we can infer from that what the concentration of lithium is. Because lithium carbonate, when it dissociates, breaks into 2 lithium ions and 1 carbonate ion. And so if carbonate 7.4 times 10 to the negative second, lithium would have to be twice that. Now, if I don't want to have to go about it that way, I can use my change in X to kind of help determine this as well. I know that lithium is going to dissociate, or we're going to make twice the amount of lithium ions as I made carbonate. And so if I know what the value of carbonate is, I know what the value of S is, 7.4 times 10 to the negative second. So I can go ahead and solve for KSP in terms of S, 4S cubed, and then I can substitute my value of S in, 7.4 times 10 to the negative second. And when I do the math through, I get that the KSP of lithium carbonate is 1.6 times 10 to the negative third. Now that's a pretty big value for a K expression, and that kind of makes sense because lithium is an alkali metal, and those metals are supposed to be soluble. So it's not going to, you're going to need a fair, not too much of it to be able to get it to dissociate. Okay? It's going to be more likely to produce ions. In this particular example, the concentration of silver ions in a solution saturated with silver oxalate, that's what C2O4 is 2.2 times 10 to the negative fourth. And we want to calculate what the KSP is for silver oxalate. So if it's saturated, we're at that equilibrium value. Our Q is equal to our K. And so if silver is 2.2 times 10 to the negative fourth, and I know that 2 silvers are made for every 1 oxalate, I can also figure out oxalate's concentration. The KSP would be silver squared times the oxalate. If silver is 2s, because I make 2 silvers for every 1 oxalate, I can figure out what S would be. It'd be half of that, 1.1 times 10 to the negative fourth. And I can put that into my K expression to solve for the KSP value, 5.3 times 10 to the negative 12. This is a much smaller K value. Only a small amount of silver oxalate will dissociate, and that makes sense since most oxalate compounds are insoluble unless they're with a alkali metal or ammonium. This next one asks us to calculate the solubility of strontium phosphate. You're given the KSP is 10 to the negative 31st, so this time I'm giving you the KSP value. I'm allowing you to ignore any acid-base properties because the phosphate ion is not going to have a significant effect on changing or having an effect if the pH was acidic or basic. So we're going to assume this is neutral, so we don't have to worry about that part. I will never give you one that you have to worry about the acid-base properties. I just wanted to kind of give you guys an overview of the solubility information. So strontium phosphate, when it dissociates into water, produces 3 strontium ions and 2 phosphate ions. So the KSP expression would look something like that. Again, 1 strontium phosphate makes 3 strontium ions, and it makes 2 phosphate ions. So I can solve for strontium in terms of 3s and phosphate in terms of 2s. And if I cube the 3s expression and square the 2s expression and combine those together, I get 108s to the 5th is equal to my KSP value. So if I want to find the solubility, the S, how much was able to dissociate, I can set that equal to 10 to the negative 31st, the KSP value that was given in the problem, and find what that solubility value would be. And I get that 2 times 10 to the negative 7th strontium phosphate is capable of dissociating. So a pretty small amount can dissociate, and that makes sense given the K value was so incredibly small. Alright, the KSP of silver sulfate is 1.2 times 10 to the negative fifth. I want to calculate what the solubility would be if you have 0.1 molar silver nitrate. 0.1 is a lot bigger than the 1.2 times 10 to the negative fifth. So most likely the amount of silver that we would have needed to dissociate if we hadn't had this silver nitrate present would be a lot smaller than that. So because we have the source of silver ions, our common ion that's present when that solubility of silver sulfate is examined, we're not going to have to worry about getting silver from anywhere else. Two silvers would be formed from one sulfate. Our KSP expression is still going to be silver ions squared times sulfate ions, but rather than allowing silver to represent 2s, we're going to say the value of 2 times s is much, much smaller than 0.1 molar. And the reason why we're able to say that, again, is that if I was going to take the square root of 0.1, that would still be lots bigger than 1.2 times 10 to the negative fifth. So if I'm saying that the 2s is going to be negligible, we've seen this before, that the 0.1 is so much larger that that's going to be the one that has the greater effect on the silver ion concentration, that's going to allow the solubility of the sulfate to be smaller. So if I go through and do the mathematics, I get that the common ion allows the concentration of sulfate to only have to be 1.2 times 10 to the negative third. And if you think about that lab we did, you remember that as we changed the concentration of the calcium or the hydroxide, the solubility changed as well. That as we reduced the concentration of one of the ions, the solubility of that white calcium hydroxide precipitate decreased. So if you have more of one of your two ions making up your ionic solid, the amount you need of the other ion will diminish, and vice versa. Okay? And this will be the last part of this final section. For which salt will, in each of the groups, will the solubility depend on pH? This is the only thing I'm going to ask you to think about with pH in terms of how the concentrations of the ions present could be affected if your pH is acidic or basic. So if we look at these three particular salts, I want you to think about ions that could be representing weak acids or weak bases. Silver is a metal, so we don't have to worry about that one. But we have fluoride, chloride, and bromide. And I'm hoping you remember that fluoride was a part of a weak acid, and so that would be representing a conjugate base. And because of that, pH could affect the solubility of that ion, whether fluoride was removed or fluoride was added. So AgF would be the one that is affected by pH. And the next one, I'm hoping it's a little bit more straightforward because you can kind of see the basic component in lead 2 hydroxide. Lead 2 chloride is made from the conjugate base of a strong acid, so that would not have any effect on pH, but the lead 2 hydroxide does. Okay? So we have one last part to do in part 2 of Unit 6, but I'm going to stop this video here and we'll do the last part in just a second.